Hey folks, I really want you to do well on the upcoming exam. And so what I'm going to do is put together a review where I walk through the solution of two problems from your homework, where there's going to be two problems on the exam that are based upon problems just like these two from your homework. And so before I go any further, I want to emphasize that you're going to be given a sheet of equations. And when you deal with kinematic motion, whether it's in one dimension or two dimensions, you're often going to be going to a set of equations where the acceleration A is constant. And so more specifically, you have the equation Vx. This could just as easily be Vy, but so we're going to do everything in X. And so X is often in the horizontal direction, but we could do all of these same equations in the vertical direction, which is often called Y. And so we have some velocity x is equal to some initial velocity in the x direction plus acceleration in the x direction multiplied by time. It's good to check the units to make sure you have your equations right. On the far left, you have meters per second. And then as you go to the right side of the equation, the first term is meters per second. And then the second term is meters divided by seconds squared, but then you multiply by seconds. And so meters over second squared times second is meters per second. So all three terms are meters per second. You have this displacement delta x, and again, this could just as easily be delta y. That is expressed as 1/2 the velocity initial in the x direction plus the velocity in the x direction at some later time. So essentially what you have there is the average velocity over that time sequence. And then if you multiply it by the time sequence, you have meters divided by seconds times seconds, you have meters. And so on the left, displacements in meters. On the right, you also have meters. Another way in which you can write displacement is the initial velocity. Every time I have those zeros, which is often called naught, it's called V naught. V naught x is whatever the initial velocity was in the x direction. And so if I take that and multiply it by time, meters per second times seconds can be meters. And then if I also add 1/2 the acceleration in the x direction, and I multiply that by t squared, that term better be in meters as well. The first two terms we've seen are in meters, and so let's think about it. Acceleration is meters divided by seconds squared, multiplied by seconds squared. So meters divided by seconds squared multiplied by seconds squared is meters, and so all three terms are in units and meters. And then there's an expression for the horizontal velocity squared equal to whatever the initial velocity in the x direction is squared plus 2 times the acceleration in the x direction multiplied by the displacement in the x direction. Let's check the dimensions again. On the far left, we have meters per second squared, so it's meters squared divided by seconds squared. The first term on the right is going to also be meters squared divided by seconds squared. And then I have 2 is dimensionless, and then acceleration is meters divided by seconds squared. But then delta x is in meters, so that's meters squared divided by seconds squared. So we have meters squared divided by seconds squared for all three terms. All right, the proviso for all of these equations is that the acceleration remains constant through the interval of interest. So now what I want to do is I want to turn your attention to problem 2.55 from your homework. I promise you that you're going to encounter a problem on the upcoming test that looks just like this problem. And so this is a problem where you have an astronaut, and before they go to the moon, they can take an object and they can throw it up in the air. And so when they do their tests on the moon, they find that the change in y, often with vertical we use y, is equal to 14.0 meters. So this is the astronaut on the Earth. So I'll put an E here so we can keep track of that. And then we are asked, okay, if that astronaut goes to the moon and they throw that same object up with the same velocity, how high is it going to be then? And so we're going to figure that out. But before we do, let's also try to make sure we jot down other things that are given to us before we appeal to our equations. We know that the gravity has an acceleration on Earth that we often call g of 9.8 meters per second squared. Now, I'm just going to call this Earth because we're also dealing in this problem with the gravity on the moon. The moon is not as massive as the Earth, and so therefore it doesn't have as much gravitational acceleration on objects near its surface. But we are told that on the moon, the acceleration due to gravity is 0.170 times the gravity on the Earth. That'll help out later, being able to relate one g to the other. Okay. We also know, because this is a toss in the air, that when you are on Earth, and when we're going up and down, we'll call it y again, and at the apex of the toss, so if you can imagine, when you throw something up in the air, it slows down, slows down, slows down. It comes to its apex, which is a momentary stop, and then it starts falling back down. So at the apex of the toss, we'll call that final. And I'm also going to put an E for Earth. That is equal to 0. Because again, apex of a toss that's in one dimension vertically is going to be 0. But that's also the case if you're on the moon. Same thing with a vertical toss on the moon. So the y direction velocity final on the moon is also equal to 0. Finally, we're also told that the velocity of y initially when on the Earth is equal to the velocity of the upward toss in the y direction initially on the moon. In other words, it's the same astronaut both on the Earth and the moon, and so they throw the object up with the same initial velocity, whether it's on the Earth or on the moon. All right, so again, it's really good to go through, look at all the stuff that you know already, and then also flag what you need to solve for. And so in this case, we need to flag delta ym. So this is how high the object's going to go on the moon. We know that on the Earth, the astronaut at some initial velocity can get it up 14 meters. But on the moon, it's going to be different because the acceleration due to gravity is different on the moon. So we need to solve for it. And you can already guess that it's going to be a larger number because the acceleration due to gravity on the moon is less. And so it's going to be able to get higher before gravity finally brings it to that momentary apex where it begins to fall again. So let's go back now and look at our kinematic equations with constant acceleration. And so it takes practice. That's why it's so important to practice these problems. But over time, you begin to figure out like which equations might be most amenable to certain kinds of problems. And so going back here, I've got displacements, I've got accelerations, and I've got velocities. And if you look at the bottom equation, I got displacements, accelerations, and velocities. And so I'm going to start with this bottom equation. And so more specifically, so let's start off with the Earth. I'm going to go ahead and do the Earth in blue. And so for the upward toss of an object on the Earth before the astronaut goes off to the moon, we can say that Vy final on the Earth squared is equal to Vy initial on the Earth squared plus 2 times g, because g is the acceleration of gravity due to gravity on the Earth. And then we can say delta y Earth. So that's how high it's going to get on Earth. We already know that's 14 meters. And I'm going to actually, because I know that gravity acts opposite the direction of the toss, I'm going to say that equals to the initial velocity on Earth squared minus 2g delta ye. Now, as for the moon, which I'll put in gray here, the velocity in the y direction final on the moon squared is equal to the velocity in the y direction initial on the moon squared plus 2g moon delta y moon. And again, it's going to be opposite the direction of the toss, and so this is vy initial moon squared minus 2g moon delta y moon. And we know that this g moon term is 0.170 g. It's 17% of what g is on the Earth. Now, I want to make a case that both the equations in blue and the equations in gray are equal to each other. And the reason they're equal to each other is because, remember, whether you're on the Earth or the moon, at an apex of a vertical toss, the velocity is 0. So that equation you see in blue equals 0, because this term right here, the y final, at the apex of the toss, that goes to 0. So this equals 0. And similarly, at the apex of the toss on the moon, that term goes to 0. And so this term equals 0. So I can now equate the blue and the gray. I can say that Vy initial on the Earth squared minus 2g delta y on Earth, we already know that's 14 meters, is equal to the initial velocity in the vertical direction on the moon squared minus 0.170 g multiplied by the height of the toss y on the moon. And remember, we were told that whether on the Earth or the moon, the initial velocity, you see here what I have in red, is the same. And so that means that this term can be canceled by this term. If I just subtracted one of these terms to both sides of the equations, I would be able to get those to cancel out. That's why I put the red strike through them. Those two terms cancel out because they're identical. I could also cancel out the negative side by just multiplying both sides of the equation by -1. And look at this. G is over here and G is over here. If I divide it by G on both sides, I get rid of the G. And so now what I have is, and by the way, I also have to have a 2 right here. Sorry about that. So the 2 cancels the 2 here. So whatever the height of the toss is on the Earth is equal to 0.170 times whatever the height of the toss is on the moon. So if I divide both sides by 0.170, the height of the toss on the moon is going to be equal to whatever the height of the toss on the Earth was divided by 0.170. That's a number less than 1, so I know it's going to be a number bigger than the denominator, and that checks out because we know the gravity is weaker on the moon. And I already know that delta y on the Earth is equal to 14.0 meters divided by 0.170. And so that's your final answer. You put that into a calculator, you're going to get a number that's bigger than 14. And again, this is a constant acceleration problem. I went back, I looked at my constant acceleration kinematic equations, and I went with the last one because it had a lot of the variables that I was given in this particular problem. So I want to do another problem for you. So that problem I just showed you, the 2.55, there's going to be a problem on the next exam that is based on that specific problem that I just showed you. So now what I want to do is what is problem 3.05. And so you encounter this in your homework as well. And so in this particular problem, you have an object that's rolling on a table, and we are told that the object has a horizontal velocity component that is equal to 0.5 meters per second. And we are also told that it has a vertical velocity component that is equal to 0.8 meters per second. So we are asked, given these components of the velocity vector, what's the total distance that the object travels in 0.5 seconds. And so t is equal to 0.5 seconds. Okay, so this is where we have to do a little vector algebra. We have a total velocity that can be decomposed into its horizontal and vertical components. So you can think of it like this. You've got some horizontal component, Vx, and you've got some vertical component, Vy, and it turns out when you add vectors up from tail to tip, like I have it set up here, this is going to be the resultant vector V. That's a right triangle. Okay, this right here is 90 degrees. That's a right triangle. And so, by the Pythagorean theorem, we know that v squared equals vx squared plus vy squared. All right? And so if I take the square root of both sides, v is equal to the square root of the square of the x component of the velocity plus the square of the y component of the velocity. Okay, and so once we're able to solve for v, which is meters per second, that's our velocity. And so we're told that it is a constant velocity Okay, so if it's a constant velocity, then we simply take the constant velocity and multiply it by the time over which that constant velocity remains constant, and that tells us how much distance is covered over that time. So we can already solve for v because we're given both vx and we are given vy. So this is equal to the square root of 0.5 squared plus 0.8 squared. And so that 0.5 squared is going to be 0.25, 0.8 squared is going to be 0.64. So that would be 0.25 plus 0.64, and that is equal to the square root of 0.89, which you could just put into a calculator. So that's our v. And so then this problem is asking, okay, well, calculate the distance it travels in 0.5 seconds. All right, so let's say that we've got our velocity v, which is the square root of 0.89. Then v multiplied by t is going to tell us how far this object rolled in 0.5 seconds. And so this is equal to the square root of 0.89, which I just showed you how to calculate, multiplied by 0.5 seconds. So that's how you would calculate the total distance. And so the key here is that you have to assemble your resultant vector with the horizontal and vertical components that were given to you. Once you assemble that resultant vector, then you know what the velocity is. You know the velocity remains constant. So by multiplying by the time duration, you know how much distance was covered in that time duration. And by the way, like, if you look at that triangle in the upper left and you're thinking, okay, well, when I multiply the square root of 0.89 times 0.5 seconds, in what direction is that actually going? It's going in this direction. It's going in the direction of the resultant vector. So you're given some of the horizontal and some of the vertical, but together the motion is actually in the direction of the orange there. And so that number you calculate, know that that's the ground that's covered in the orange direction. So those two problems, which is 20% of your upcoming test, because there's 10 problems in the test, those two problems come from your homework, and I promise you, you will encounter two problems on the upcoming tests that look exactly like that. So I hope that this review can help you prepare for the upcoming exam, and I really, really do hope you do awesome on this upcoming exam. I wish you all the best on the upcoming exam. You take care.